Hello everyone, this is Bradley. Today this is a tutorial for this text dissolving effect. It has been a long time. I'm not sure people has already made a tutorial for this or not. But this is also a quite simple setup. So let's start. So here we're in Blender. As always, I'm going to use the presets which you can download for free from the link in the description. It's very important to have the presets, and I'm going to explain why later. Firstly, let's start with a plane, and I want to discuss the principle of simulation zone. Simulation probably reminds you something like physics, rigid body, soft body, closed simulation. It can also remind you about particle simulation like fire, smoke, fluid. But the simplest form of simulation is just a loop over time. It means, for example, if I have a set position and I try to offset 1 meters every frame, so what it happens is that you can add set position, set position, set position, set position, set position. You keep repeating this process as we are moving through this timeline, and you are going to have an animation. This is very stupid to do in real life because you are not going to really replicate all this kind of set position every frame. So instead, what can happen is you are putting these simulation inputs and the simulation output to include this set position. And within this serial loop, the simulation output will output this resulting geometry back to the simulation input, and you repeat this process again every frame. So now if we try to play this animation, you can see this plane is actually moving on the x-axis with this offset 1 meter per frame. Okay. In real life, however, it's not always necessary to use the simulation zone, because in this particular case, what you can do is just to keyframe offset 1 meter and 101, and you're going to have basically the same animation. Okay. The reason I mention about this is to emphasize the fact that simulation is not a solution to every question. It definitely opens a lot of possibility when you're working with geometry nodes, but it's not always needed. Recently, when I'm working with my project, I never ever thought to use simulation because it's just not necessary. So planning ahead about what you need to do and what kind of tool you need is really important when you are working with your own project for the clients. So why do we need simulation nodes today? Because we are working with something that you cannot keyframe, that is noise texture. Noise texture is driven by the vector from your inputting geometry. Here, instead of using the initial grid, let's make a procedural grid so that I can control the amount of vertices and probably increase the size as well. And then let's take the set position. By adding this noise texture, you can see it becomes very noisy. And we can visualize this noise by using the viewer node. You can see all this kind of color within the plane. Okay, so this is the noise we have, which is basically a random value in each XYZ channel. Or you can call that RGB. It's the same. Okay. And since we cannot really keyframe the vector driving it, we need a simulation input and output. If now we play this animation, you can see it always going in a positive direction. This is because when this color is generated, it's always 0 to 1 in 3 channels. So what we can potentially do is to subtract that by 0.5. And to make it more particle-like, let's take a mesh 2 points. So now if we play this animation again, you can see, we see it, but there are some particles, they stay at a location and they no longer move. The reason is that when we visualize this noise texture, when it's generated, there are some black areas being made. And if the offset becomes 0, 0 now, the offset will be 0, 0, 0 later. So this comes to be a problem, and to solve that, we need a very sophisticated formula. Houdini tutorialist Antagma spent 26 minutes in his tutorial talking about this concept of crinoids. And here I'm basically just taking his node tree, what he made in his tutorial. He has kind of 6 noise texture because we need to do a kind of a subtraction on the x, y, z to make a partial derivative. It's a very complex concept, and just by looking at the node tree, you know it's a very crazy thing. There are so many different linkages here and there, and it's also a mystery of all these kind of weird wires. I do not understand a shit of that, so I'm just using his node tree. I do not understand mathematics, so I don't care. That's why a preset is so important, because if you are not using presets, you still have to build this thing. Either you're watching his tutorial or you're watching other people's tutorial. This is not avoidable. In the future, I believe Blender developers will make a node for you, but for now, it just doesn't exist. You have to build your own or take from somebody, like right now. So once we have this crinoid turbulence, and by playing this animation, you can see they no longer converge at a particular point, and this is just a kind of beautiful noise. It becomes less beautiful when it's too divergent, but it's okay for now. But this is not the end of this tutorial, because I want to add some trigger. Now you can see that all particles are moving at the most beginning, and they are on at the same time. I want to add a kind of a trigger to control precisely when the simulation should start for every particle. And to do that, let's think about the reason it's moving. So we have this scale of 1, 0, and 1, which means we are moving this particle. So when the scale is 0, then all these kind of particles will not move or being offset within this animation. When it's 1, they will start to simulate again, which means you can potentially keyframe this scale. Maybe we start at 0. So let's select this node. And let's make the keyframe constant, and maybe scale at 1, and let's add a keyframe. So initially there is no simulation, but after a second keyframe, they start to simulate themselves. Okay. But this is still a simulation for every particle. But you know the concept. Okay. So here what we can do is we're going to use a for. I've made a tutorial talking about this proximity for, which is essentially just the proximity, just the geometry proximity, or this is the distance vector math. Whichever way, you're getting a distance value somewhere. Okay. So in this case, I'm going to use this for into the scale or for. They are essentially the same. So let's plug that into the for. And I'm going to use an empty. It will be better to be a spherical empty. And let's lock this plane. So the idea of proximity for is closer to the center of this empty. It will give a value of 1, and outside it will be a value of 0. So now, by playing this animation, you can see that in the middle there is a simulation, but outside there is no simulation. So this is the idea of proximity for. And you can play that, for example, you can enlarge that, you can see that they start to move, but you can also see they stop the simulation once they are outside the area of this proximity for. So they just freeze. Okay. Sometimes this may be what you want because it looks kind of a painting effect somehow. Let's decrease it. So you can see this is kind of a painting effect. Quite interesting. But at other times you may not want it. You want to trigger the simulation forever, once for all. Therefore, we need a switch. So let's take a greater than 0. So if this fourth is greater than 0, then we're going to output that. As previously mentioned, this entire simulation is a loop. You output this geometry back to the simulation input. This is similarly to all these kind of other outputs. You have this kind of result. We can name that as a trigger. We are outputting this trigger back to the initial trigger as well. So within this node tree, you can see the previous trigger is actually the information from last frame. If there is no information from last frame, then it will use the trigger outside this simulation input. Okay. So here, let's take a switch. This is a very important concept because it may be confusing since the linkage is not really linear, because we input information here and this information go back there and this information go back here. So it's kind of very confusing, but you really have to understand that. Switch is probably one of the most common nodes being used when you're working with simulation because there are so many conditions. Okay. So what happened here is that if the fourth is triggering the simulation, then I'm going to use this trigger for the future. Otherwise, I'm going to evaluate this trigger by the proximity fourth. And then I'm going to replace it. And of course, I'm going to use this output to the fourth as well. So this becomes to our new node tree. So now if I play this animation, you can see there's something weird happening because there are some displaced points, but they aren't having their simulation for some reason. The reason comes to the most basic principle of field, that although these two linkages come from the same node or the same output, but they are actually representing different values because the geometry linked to that is different. This is because the position attribute, which is input in this custom vector, is being manipulated by this set position. So the evaluation is different. So to solve that, the easiest way, I think, is just to capture an attribute. Let's capture Boolean, and we're going to use this Boolean to replace it. So that we're getting a evaluation status at this particular geometry to make sure these two linkages are 100% the same. So now if I play this animation again, you can see we won't have the previous problem. And once the animation is triggered, they are really triggered. Even if they are moving outside my spherical fourth, they're still moving. Okay. Right now, you may realize that the entire animation is very, very fast. This is because we are almost moving 1 meter per frame. And within this setting, we are having 30 frames per second. So we are moving 30 meters per second, which is very, very fast. It's almost like a car or bicycle, whatever. Okay. So we need to reduce this amount. That's why I need a value precision. So if I 2 10th exponents, which means 0.01 right now. So if I type in 5, this is 0.05. So this is just to give a kind of a small value so that we can have a kind of slower animation so that you have more time to enjoy it before it goes to be very crazy. Okay. But this is not the end of this tutorial. I still want to kill these particles, otherwise these particles will just flow within this entire viewport infinitely. That's why we need a set point radius. So by changing that, we can increase or decrease the scale of it. And we're going to kill that over time. There are many different ways to do that. And I'm going to tell you a method which I do not really like, but it's probably easier for you to understand. So firstly, let's just replicate this value precision, because fortunately we already get a value of 0.05 here. And let's name that as radius. And I'm going to use this radius to set point radius. And in order to form a correct loop, I'm going to output that later. You may wonder what I'm doing here, but here I'm going to add a math and multiply with 0.9. And then by playing this animation, you will see a very interesting effect that everything is disappearing. This is because, for example, initially this radius, assuming it starts at 1, and after one frame it becomes 0.9. And after another frame it becomes 0.81. And in the fourth frame it becomes 0.721. Something like that, I think. And it becomes smaller and smaller until it's barely visible in the viewport. So this is the principle of it. But of course, right now we're having this simple formula to make every particle disappear. How can I make this particle disappear only after they are being triggered and moved with this turbulence? We're going to use the switch we formed previously. You can see the switch node is so important. That's why I said it's probably one of the most common nodes being used within simulation. So if it's being triggered, then we decrease the radius. Otherwise, we just keep it as it is. So now we output this radius, and let's try to see this effect. You can see only those points that's being moved will disappear. And you have this kind of disappearing effect. Okay. And now you probably realize this 0.9 is quite bad. Let's make it 0.98 so we can have a slower disappearing animation. And you can see that. Okay. So there are lots of values that you can potentially tweak, but that's basically the idea. Okay. Here we basically finished this entire tutorial. Although you may ask, hey, this tutorial is talking about text dissolving effects, but there is no text. I have to remind you, this entire tutorial is just an example, and everything is procedural. So I'm starting with a grid, but it can be a cube, a sphere, or even a text. So let's start with a text. Let's create a new node tree. And let's delete the initial grid and the mesh points. I'm going to use a string to curve. So let's take a blender. And I need a middle. And transform it. Transform by 90 degrees so that I'm looking at it. I also need a, let's say, this fill curve to make it a mesh, and I need the solidify modifier to make up the thickness or volume. Okay, and I'm going to point distribute. The point distribute essentially is actually the points distribute on face. The only difference is it's using density, but I'm using the amount, so I can set the amount. But even by setting 10,000, I do not see the points. This is because I have to realize the instance. Okay. But I have to remind you, this is distribute point on face. So if you want to distribute everything in volume, you need to distribute points in volume, and because the mesh is not working for volume, so you probably mesh to volume as well. It becomes very complicated and expensive. I'm not going to discuss here today. Okay. And we can plug these points into place. So now if I play this animation, there's no animation, but if my stuff is moving, oh, it's not working because I didn't connect that. Yes. So if I connect everything, then you can see the taxi is moving, and basically that's it. There's also one tiny thing I want to remind you that right now we're only using a noise to drive this entire animation, but you can definitely tweak that. For example, I can add a vector math, and I can take a combine x, y, z to make it fly on the z-axis constantly. And I definitely need a math to multiply with it. So now, if I start it, you can see they're flying away and they finally disappearing as they are skating down themselves. So this is the idea. This is the procedure you can play around all these kind of settings. And this is it. I hope you enjoyed this tutorial. I'll probably see you next time. Bye-bye.